Welcome back to a course on measure theory and integration. In this lecture, we will start with the result that is the collection M is a sigma algebra. Okay, we are about to prove this theorem. This is basically a theorem. So we are about to prove this theorem, but before proving this theorem, I would like to recall the definition of sigma algebra. Okay, sigma algebra on a set X means what? First of all, we'll have to take some collection. Okay, so M be any collection of subsets of X. Okay, so we'll have to collect few possible collections of subsets of X. Okay, and it has to be closed under countable union. Okay, the second condition is closed under complement, and the third one is closed under finite intersection. If these three conditions are satisfied, then we say the collection script M of subsets of X as a sigma algebra, right? So here the collection M, what is the collection M? So formally stating, here the script M is the collection of what? Collection of measurable sets. Okay, so here we have the collection of measurable sets, and we'll have to prove this collection of measurable sets is a sigma algebra. So in order to prove this, if you revisit, okay, this is the definition of a sigma algebra. We'll have to prove these three conditions. First of all, let us revisit the results that we have seen already on measurable sets. Okay, here you see a set is said to be measurable if this condition holds for any set, right? And we proved here set of outer measure is measurable, union of finite collection of measurable sets is measurable. So basically the things that we have proved. Okay, here what are the things that we should prove? So you people can just extend, or you can just replicate the proofs here. So I am not doing those things, so let me just write them as claims. Okay, the first claim is finite union of measurable sets is measurable. Okay, next thing, we'll have to prove the complement. If E is measurable, then so is E complement, right? So by the measurability of E, what do we write? For any set A, we have M star of A is M star of A intersection E plus M star of A intersection E complement, right? So now what I'm going to do is that let me check the measurability of E complement. Okay, to check the measurability of E complement. So in order to do this, I observe E complement, the whole complement is E itself. Therefore, M of A intersection E plus M of A intersection E complement shall be written as M of A intersection E complement the whole complement plus m of A intersection E complement, right? So this is nothing but m of, sorry, actually these are m star, right? So we are talking about the outer measure. M star of A intersection E complement plus m star of A intersection E complement the whole complement, that is nothing but RE. So this quantity is equal to m star of A, right? So this is equal to m star of A. So this very well tells us that, tells us what? E complement is measurable, right? Now we'll have to prove finite intersection of measurable sets is measurable. So how are we going to achieve this? Let us revisit one of the results that we proved. Okay, so if we have a finite disjoint collection of measurable sets, this happens, right? And by this, what are we trying to convey? Okay, anyway, we proved the thing for complement and union, right? So as a result, this will easily follow. So this follows from De Morgan's law, claim 1 and 2. Okay, it is just the application of these three would give us the third one. Now, so with which what we conclude is that, therefore, we come to a conclusion that M is a algebra. Okay, we proved the collection of measurable sets is an algebra just by proving all these things. Now it is left to prove, okay, it is left to prove the measurability of union. How are we going to achieve this? Okay, let me take here, let E be the union of countable collection of pairwise disjoint measurable sets En. Okay, here what are we trying to say? That is EI intersection EJ is empty for I not equals J. Okay, whatsoever the value of I and J, if they are different, then the intersection is empty. That is what we mean here. Okay, and the thing that we said when we write that in notation, E is the union of these sets. Okay, so this is what is taken. Now let us take, let A be any set and let F denote the finite union of the sets in the collection. Okay, now we have to prove E is measurable. So in order to prove E is measurable, what are we going to prove? It is enough to prove M star of A is bigger than or equals M star of A intersection E plus M star of A intersection E complement, since the reverse inequality is trivial for any kinds of sets. Okay, Here E is a countable union and F is a finite union. Therefore, F is contained in E. Okay. So I think I'll have to give you some diagrammatic ideologies. Let this be my E. F is contained in E. So this is my F and this is my E. So this is my whole space. Now I'll have to look for E complement and F complement. So E complement, let me shade in green color. Okay. This is my E complement. Right. When I take the F complement, that let me do it in purple color. You may very well see. Right. So this implies you have your F complement and E complement. Now you see the inclusion. Your F complement is the bigger set, right? So your F complement contains E complement. Fine. Okay. Let me mark this as equation 1. Okay. This is to be used in the future. So let me mark this as equation 1. Okay. Uh, we just proved M is an algebra. Okay. So using the fact that M is an algebra, we said that F is measurable. Why is it so? Since F is a finite union of measurable sets. Since it is a finite union of measurable sets, it is a measurable. Again, we say that F complement is also measurable. That is, F is measurable will imply F complement is measurable. Since we proved it is an algebra, right? We get these things. Okay. Now we make use of the measurability of F complement. Okay. So the measurability of F complement gives M star of A equals M star of A intersection F complement plus M star of A intersection F complement. The whole complement is simply F. So let me write that too. So A intersection F complement plus M star of A intersection F. I just rewrite them and here I'll have F and let me have F complement here. Okay. So let me mark this as equation 2. Now I see that uh, consider M star of A intersection F, which is nothing but M star of A intersection union I runs from 1 to n EI, right? So this is nothing but summation I runs from 1 to n M star of individual A intersection EI. So this is what we proved in the previous lecture, right? So this is happening to be true. Since all these E1, E2, etc. till En are measurable sets, this happens to be true, right? So um, now I'll have to make some observations and I'm going to plug in some informations into it. Here, my A intersection F. Okay, let me do it in different color. Here, my A intersection F is a subset of A, right? So this tells us that outer measure of A intersection F is smaller than or equals measure of A, right? So what I get is that outer measure of A is bigger than or equals m star of A intersection F, which is equivalent to summation I runs from 1 to n m star of A intersection EI. Right? Okay, this is there. Even if I add some quantity here, this still remains the bigger one. Okay, so I just add outer measure of A intersection E complement. Right? This is here. Why is it so? Okay, so here, just a minute, just a minute. Mm, just a minute, I'm just going somewhere wrong. F is what kind of a set? F is a measurable set, right? So we just wrote, okay, I think we don't need these ideologies. We can make use of our equation 2, I suppose. So let us revisit our equation 2 that tells us that this is happening to be true, right? Okay, so my by 2, what I say is that, what is my 2? That is outer measure of A equals outer measure of A intersection F, that shall be replaced with summation I runs from 1 to n m star of A intersection EI, right? Addition with, what is the term that I have there? That is A intersection F complement. Sorry. So this is going to be m star of A intersection F complement. Okay. Now I notice that E complement is contained in F complement. This tells me that A intersection E complement will be contained in A intersection F complement. So this will tell me that outer measure of A intersection E complement is smaller than or equals outer measure of A intersection F complement. So I am just going to plug in this into the previous expression and I get m star of A. This quantity is going to be there as it is. Summation I runs from 1 to n m star of A intersection EI. Okay. Instead of this, I am going to have greater than or equals. So bigger than or equals plus m star of A intersection E complement. Okay. So here, since the left hand side of the above inequality is true for all n, we have outer measure of A is bigger than or equals summation I runs from 1 to infinity m star of A intersection EI plus m star of A intersection E complement, right? So this one is what? M star of A bigger than or equals m star of A intersection E plus m star of A intersection E complement. So with which what we proved. So this is what we intended to prove. Therefore, E is measurable. What is E? Countable union of measurable sets as measurable. So script M is a sigma algebra and this completes the proof. The next lemma. So this is a lemma. The next lemma that we are going to see is the interval a to infinity is measurable. Okay, so how are we going to start the proof? Let us see. Let's a be any set. Okay, so what should we prove? We will have to, in order to prove the measurability of this a, measurability of this interval, we'll have to prove m star of a is bigger than or equals m star of a infinity intersection a plus m star of a intersection a infinity complement. So we'll have to prove this one, right? So in order to prove this, what we are going to do is that we will again suppose a1 to be the set a intersection a comma infinity, and a2 be the set that is a intersection minus infinity comma a, or in other words, this is a intersection a comma infinity complement. Okay, either we may say this way or this way, it is up to us. Okay, so it is up to us. Now to prove what, the claim is to show outer measure of a is bigger than or equals m star of a1 plus m star of a2. So this is what we'll have to prove. That one we just simplified and wrote in this way. Fine. Now to proceed with the proof, if m star of a is infinity, then there is nothing to prove. The proof is obvious in this case, right? Next, the case is if m star of a is some finite quantity, then you may be given with some epsilon positive. You can identify a countable collection in. So the members of this collection are of course open intervals. That is what the definition of outer measure tells us, right? Which this collection cover the set A, and for which summation, okay, for which what happens, m star of a is the infimum of summation L of in, right? So from this we squeeze out some information. When we take the infimum, which means what, we'll have to add some quantity to the outer measure, because among this possible values the lowest one, okay, the greatest lower bound is the m star of a. So when you add some quantity to this, you can balance this infimum actually. So this is what we get. Okay, now let us again redefine something. We are actually defining, sorry, I said redefining, we are defining something. In prime is in intersection with a comma infinity, and in double prime is in intersection with a comma infinity complement. Okay, so either complement may be written in this way, or we can write it this way as well. It is up to us. So this is nothing but in intersection minus infinity comma a, right? So from the way in prime and in double prime are constructed, it is very obvious that in prime and in double prime are intervals. Okay, sometimes they may be empty as well. And what happens, what is the outer measure of the intervals? That is L of in may be written as L of in prime plus L of in double prime. This is the outer measure of these two sets. Right? Now we notice that this A1, okay, that is the set. A1, which is nothing but what? A intersection this quantity which is contained in A, and this is contained in the union In. Right? So since this is happening to be true, we have m star of A1 is smaller than or equals m star of union In, which is nothing but smaller than or equals summation L of In prime. Okay, L of union In prime. This is which is contained in A, which is contained in union In. So I'll have to, okay, yeah, I'll have to treat these two things, and In prime is only this part. So I'm just making the union. Okay, so we can just, okay, if you just look back here, your In prime is the intersection of In with A to infinity. Your An, of course, your okay. Let me do that calculation here itself. You will get the idea. So this is contained in union In, right? Fine. So here what we have is this A intersection A infinity will be contained in this A itself is contained in union In, right? So you will have to make intersection with A to infinity. So when you make intersection of each In with A to infinity, you will be left with what? So union of In intersection A to infinity. This is what you have. So this is nothing but union of In primes, right? So just because this is happening to be true, we can write m star of A1 is smaller than or equals m star of union In prime, which is nothing but summation length of In prime. Okay. Similarly, A2 will be contained in union In double prime, and hence m star of A2 is smaller than or equals m star of In double prime. Okay. So I think I'll have summation also. Summation m star of In double prime. Right? So what is that next? We'll have to just add these two things, right? So when we are about to add these things, that is outer measure of A1 plus outer measure of A2, both are smaller than summation m star of In plus summation m star of In double prime. Actually In prime plus In double prime. So these are nothing but summation length of In prime plus summation length of In double prime. Okay. So if you just revisit the way in which we constructed In prime and In double prime, okay, we have this bar here. So your In prime, wherever your In prime ends, there your In double prime starts. Actually, the reverse way is happening here. Wherever your In prime, In double prime stops, there your In prime starts. So when you make the union of these two things, you may very well notice that this is summation length of In prime plus In double prime. Whether you just find the interval and take a length and finally sum it up, it is same as that of just making the union of those two intervals and finding the length. That will happen to be the same, right? So this is nothing but summation length of In. This is smaller than or equals measure of A plus epsilon. And as usual, we come to a conclusion using the fact that since epsilon is arbitrary, m star of A1 plus m star of a2 is smaller than or equals m star of e. Actually, we'll have to write it in the other sense. Even if you don't write it in the other sense, that is perfectly fine, right? So a1 plus outer measure of a2. Thus, we conclude that therefore the interval. Okay, just a minute. Therefore, interval a to infinity is measurable. So this is what the agenda for this lemma. We proved it. Next, we are going to see the definition of Borel sets.
A collection script B of Borel sets is the smallest sigma algebra which contains of all of the open sets such a smallest sigma algebra exists, and it is also a smallest sigma algebra that contains all closed sets as well. So it also contains the smallest sigma algebra that contains all closed sets and the smallest sigma algebra that contains all the open intervals. Okay, and the smallest sigma algebra that contains all the open intervals. So here you will have to pay attention to identify what do you mean by open sets and what do we mean by open intervals. Okay, in the course on real analysis, every open interval of this form is an open set, but every open set need not be a open interval, right? Because we have the concepts like arbitrary union of open sets is open, arbitrary finite intersection of open sets is open. If you have an open interval of this form and you have another open interval where the intersection of these two things may be empty as well, right? So with this condition, this is an open set, this is one of the open set, but this is not an open interval. Okay, a Borel set. Okay, initially we have seen the definition of a Borel set, which is the smallest sigma algebra which contains all of the open sets, which means all possible open sets are collected inside the sigma algebra. Such type of sigma algebra exists. Inside that sigma algebra, not only the open sets, it will contain the closed sets. Closed sets in the sense, not only closed intervals, some finite union of intervals of this form and arbitrary intersections of intervals of this form are also closed sets. These are some results in undergrad real analysis. So with these ideologies, we say these things, right? Okay, what I'm trying to say here, all possible open closed sets are there in the smallest sigma algebra, and this sigma algebra will contain the all possible open intervals as well. When we say all possible open sets, obviously open intervals are part of open sets, right? So these things are happening to be true. I think these are some ideologies. If you need, I can just keep it here. Actually, what we are about to prove here, we are about to prove a Borel set is measurable. In particular, we'll have to prove open sets and closed sets are measurable ones. Right? So let us start the proof formally. So in this proof, we start by noting that the collection script M of measurable sets is a sigma algebra. Right? So here we say that the Borel set will contain all possible open sets. Therefore, I make use of the measurability of this interval. This is measurable. Therefore, the complement of this set has to be measurable. So that is a comma infinity complement is measurable. That is minus infinity closed at a is measurable. So in the place of a, we can have any finite value, right? So is measurable for any real value a. Now let us consider minus infinity closed at b, or I can have it as a open intersection a comma infinity. This is nothing but this quantity interval ab, right? Now also I write minus infinity closed at b. Do I have closed? No, I should have open. Yeah, union n runs from 1 to infinity minus infinity comma b minus 1 upon n. When n approaches infinity, it will approach to b. That's it. Okay, so I'll have to close this. Yeah, so this shall be written as like this. Here, we know that this is measurable. Even if I lose 1 point from it, that doesn't bother. That doesn't concern for the measurability. Okay, I'm just removing only 1 point from it. Okay, so here what we have is minus infinity comma b is measurable. Okay, measurable. Okay, we have this one. Now what we wrote, okay, this is equation 1, right? So by equation 1 and the fact that finite intersection of measurable sets is measurable, we come to a conclusion that the segment AB, that is the open interval AB, is measurable. Okay, uh, since no restriction upon A and B are imposed, so this clearly tells us that any open interval is measurable. So we just proved that open intervals are measurable. We have not proved open sets are measurable, right? Okay. So for which what are we going to do? Here we just use some facts from the real analysis. That is, each open set is the union of countable number of open intervals. Okay, and we also know that countable union of measurable sets is measurable. So, with which we can conclude that every open set is measurable. Okay, so next what? Next, we make use of one more property. If A is measurable, then so is A complement. So, with which we write complement of open sets are measurable. What are the complement of open sets? That is, closed sets are measurable. Okay, we just proved open sets are measurable, closed sets are measurable using some results in real analysis. Okay, so finally, what we are coming to say, uh, Borel sets are measurable, right? Thus, Borel sets are measurable. So, with which we conclude the theorem. And I would like to present a definition here. So, this definition is the definition of Lebesgue measure. If E is a measurable set, then the outer measure of E is called a Lebesgue measure and is denoted by simply ME. Right? So I stop this lecture by this, and in the upcoming lecture, we are going to see few more theorems and propositions based on this measurable sets. Thank you.